Okay, let's get started. We have delayed the test by 1 day, and so that means today I will finish up all of what we're going to do in Chapter 10, and what I have left to do are confidence intervals and prediction intervals on predicted values from a regression model, and I need to do the ANOVA table. Right, which is something you don't hit in MA343, so that'll be new to you. But
can I ask you to maybe consider putting the remember the practice versus the graded stuff on the online stuff? Mm-hmm. Could you put those back up so that I could kind of do unlimited attempts and review that way?
Well, see the problem. I really can't because I've given up on their AQ questions, the algorithmic questions. I mean, they're so full of errors. And I was making this homework set, and I was finding more errors. And I thought, okay, I can only use their exercises, which are verbatim out of the text. But then if you have a practice set, then all you got to do is write down what the answer was. Go in, it'll be exactly the same numbers, exactly the same answers when you go into the graded.
I was talking about the old, the stuff we've already turned in from previously. Because it closed it up when it became due. The practice of the graded. 9192, yeah.
I think you can still get to them.
Me neither. I looked.
Well, I'll look and see if I can figure out a way to put them back up.
I appreciate.
Yeah, because that is handy. But you just have to be aware there will be some errors in there. But so last time, remind me where I left off last time.
It was
something about confidence intervals and degrees of freedom.
It was confidence intervals for B sub 1, cheat-crit, standard error, B1.
Yeah. Okay, so I forget how to. I think there's a way. Yeah, there we go. I can go backwards if I do this the right way, but I guess it only let me do it once. Let me just go through. It'll work. I went through all this last time. This was the thing I drew by hand because I couldn't find it. Well, I recreated it and I put it in there. And what this is a picture of all the semesters dated together. And there's a legend down at the bottom that shows which semester. And if you can decode the colors of the lines, then go for it. But there's just too many in there. But notice that most of the lines are pretty similar to each other, but there is variability. They don't all have exactly the same slope. Some are tilted a little more than others, and you see this kind of bandwidth of a little wide out here on the ends. It gets closer together in the middle, and then it's a little bit wider out here. Right?
It also doesn't look like they're accessing. It looks almost like they're stood off a little bit.
Yeah, I'm not sure what you mean by that, but you mean that they're not exactly going through the same point.
Yeah,
yeah.
Like they're kind of
and they wouldn't be. I mean, think about each semester's worth of data. The line must go through what point?
The mean of y,
mean of y and mean of x. So the point x bar, y bar. And what's that point called? Have I given you this word? The centroid. I might not have said it yet.
No, not yet.
But the centroid is... it's going to go through the centroid of that semester's data, right? So each of these lines is drawn without looking at all the other lines or all the other semesters worth of data. So they each have their own centroid, so they don't all go through the same point, right? So that's fine, but think about the implications of what this graph shows. It says the slope varies from sample to sample to sample, right? Not a lot, but some. And the intercept changes from sample to sample to sample. So in other words, that doesn't work. There is a way to make that work too, but darn it, now I gotta go. I have to use the mouse. So I'm not smart enough to figure all this out. There. And Leanna couldn't be here today or Monday to tell me how to use this thing, but she knows how to make it so I can write on there. But anyway, the slope changes from sample to sample to sample. So this next slide shows for all of the semesters, there's actually more semesters above this, but I limited to these for this picture. Here is the value of the intercept for each of those lines and the value of the shoe size for each of those lines. Right? So you see some variability. Not a lot, but some variability. So in fall of 2008, it was 1.64 was the slope. Okay, now let's put back on our, what am I looking at, our interpretation hat. What does that number 1.64 mean? Exactly. Very good. So if I have a size 9 shoe and somebody else has a size 10 shoe, I would predict they'd be 1.64 inches taller than me. Right? And every semester it's around that same value. Some semesters it's smaller, some semesters it's bigger. Right? So this one's 1.54, this one's 1.74, there's a 1.8. So there's some variability there. Right? Well, the next slide shows I took those 17 slopes and those 17 intercepts from different semesters worth of data, and I said, what's the average of all of them? And what's the standard deviation of all of them? Well, this standard deviation is the variability in slope. Now, I gave you a formula for variability of slope last time. Do you remember that? The standard error of the slope. Standard error of B1. What was that formula? What did you say? The square root of
Square root of sigma squared variance.
Okay, and so that's sigma, right? So it's SE over
And square root of n minus 1.
right, square root of n minus 1 times SX, right?
Yes.
Right. So the variance is this thing squared. So you'd have SE squared on the top, the square root would go away, and then this would be SX squared. But then standard error is that, right? Now, this is based on one sample worth of data. This is B1, not beta 1, right? A sample statistic. So I could compute this value for each of those regression equations. The thing that I don't think, actually maybe I do. Nope, I don't. I thought I still had SAS up and running on here, but I must have closed it out. But I went to one of those 17 regressions, and it gave me the standard error as part of the output. Right? Actually, let me just take the time to go back and do that. Have I demonstrated using SAS with the Enterprise Guide?
Yes.
Okay. So I don't have to do this. So I'm just going to launch SAS directly. And unfortunately, this is so slow. It's hard to do with class staring at you. I do all these on my own computer when I'm in my office because they run so much faster. But
a quick question with the idea of the centroid.
Okay, go ahead.
If you do that and you show that the centroid is different for the individual samples, wouldn't that be evidence for the randomness of your individual samples?
Okay, I was clicking and not listening. What did you say?
I said about the centroid of the individual samples.
Uh-huh.
If you show that the centroid is different for all the individual samples, would that not be evidence for the randomness of your individual samples?
Yeah, exactly.
Good. Thank you.
That's exactly right. The samples will be random from the population, so they each have their own centroid, but again, they should be close as long as you have a reasonably good sample.
And if they're not, then the individual samples weren't random enough.
Yeah, I guess you could say that. So let's run. I got to remember where it was. Down here at the bottom. I'll rerun what I produced that plot from, or that table, and let's say, I'll tell you what. Bear with me, I'm doing a little coding here. Can you see what I'm typing? So where semester equal spring 16. So I'm running this proc reg. You can do the same thing with Enterprise Guide, but this is just faster for me. Uh-oh. I got to now check my log window to see what spring. Oh, let's go back and look at. Nope, not there. This spring 2016. That looks like I spelled it right, doesn't it?
Did you do 2016 or
Yeah, I think
16?
16.
Try SPR.
Oh, got it. Yeah, so this has to be 2016. Okay, now it's kind of slow running here, so while it's running, what this is going to give, okay, so we'll need this later today, but I want to go up. Can I go up to this? Look at the standard error that it gave for the slope, right? So for the slope, it says 0.05565. Now, if you remember from this, that the overall standard deviation of the 17 slopes was 0.0767. Those numbers are fairly close. So the standard error computed from one single sample using that formula I wrote on the board over there is very close to just the overall variability from only 17 different semesters. It's not exactly the same, but the reason it's not exactly the same is because this is only 17 of the infinite number of possible samples you could have gotten. Right? So now let's go back to this output and see how to compute that number. Right? So using that formula, I need SE on the top of it. So where's SE? Where do we get SE? SE is the estimate of the standard deviation of the residuals. Right? It's often called the standard error of the estimate, which I don't like that term, but just standard error of the model. But I gave you a formula for it last time, or at least pointed at a formula on the slide I was showing. But SE is the root mean squared error, which is the square root of the sum of squared error over the degrees of freedom for error. What? I've not heard these things before. Well, looky here. This part of the model is called the analysis of variance, and it has sums of squares and then mean square. So SSE, sum of squared errors, right? Well, remember last time we had the sum I equal 1 to n of e sub I squared. Sum of squared errors. So that's this thing. Now the mean squared error says, okay, take the sum, divide by how many you summed up, and you got a mean. So the mean squared error divides by its degrees of freedom. It's not dividing by n, and this is not the right class to go into the theory of why that is, but it's kind of it's not self-explanatory, but just in a nutshell, there's 2 degrees of freedom missing from the total sample size because to compute this residual, we have to first estimate the slope and estimate the intercept of the line. Then I can see what the residual was. So each of those estimates takes away a degree of freedom from the sample size. So you divide by degrees of freedom instead of by n so that you have an unbiased estimate of the population variability. Stay tuned in MA344 to get a better explanation. Actually, that's probably MA345. But okay, so this is called the mean squared error. Right? Now, written out as a formula, I could write it as, instead of E sub I, what is E sub I? What's the definition of a residual? Well, it's the observed value minus y hat, the predicted value. So that's the mean squared error. Okay. Okay, now where was I going with this? We were going to compute this thing. So I got the top part now. I know how to get it. It's the square root of the mean squared error. So let's put that number in. Do it on your calculator for me. Actually, you don't have to, because looky here. It says right here, root mean squared error. Now, why do you suppose they gave me that? Because it's a number that gets used a lot. So they say, well, we won't make you compute it with your calculator. We'll just give it to you. So root mean squared error is 2.25562. I already forgot. Read it to me.
2.25562.
Okay. And then n. What is my n here? Look at the degrees of freedom for the terms in this ANOVA table. I'm going to come back and give you formulas for this ANOVA table in a second. But the total degrees of freedom, right up here it says, number of observations used, 400. So the total degrees of freedom is n minus 1. The error degrees of freedom is n minus 2. So you can always look at that and go, oh, it's n minus 2, add 2, and that tells me what my n was. So I need the square root of n minus 1. So I need the square root of 399. So the only number I'm missing is the standard deviation of the x's. So my x variable is shoe size. How do I get the standard deviation of the x's? Well, if I'm in SAS, I go into the describe and then summary statistics, set them all up the way you want. If you're running the SAS code, it's easier than that. I can just do a real quick proc means. And I got to add this where statement so that I'm doing only the correct semester. And then variable shoe size.
What you did just blew my mind.
Yeah, don't worry about it. So here's the results of that. And I can't get that to go up because I've scrolled all the way to the bottom. But it says I have n equal 400. And the mean shoe size was 9.56675, which sounds reasonable, right? 9.5 shoe. That's pretty average for this data. Standard deviation, so that is SX. Right? Standard deviation of the X variable. So 2.029. 2.029. I'm stopping at 3 decimal places there just because I'm out of room. But so now do that for me on your calculator. Oh, my thing didn't follow. You got a question?
So the MSE is the stuff down there, the sum of
Right.
E. So is the square root part of that?
Yeah.
That's what I want
There you go. See, I do things like that on purpose just to see if you're paying attention. Not really, but.
to know. Your answer.
What's that? You got an answer?
0.0556.
So I'll write it up above here. 0.0556.
54.
And then a 5.4? Okay, out to that many decimal places. Now let's go back to our ANOVA table. And it's got 0.05565. So within round off error, that's how that number is done. Now out here, I had to give SAS an option. I had to specify an option to ask for confidence limits on the parameters. So where does 95% confidence limit on 1.68 come from? How would you compute that? How are all confidence intervals computed? You- Okay, good. You take your point estimate and you add and subtract a critical value times, the margin of error, which is a critical value times the standard error. So all we need to know is what's the T critical value for 95% confidence and error degrees of freedom. So the confidence interval, let me erase this stuff. Confidence interval for slope is B1 plus or minus T with n minus 2 degrees of freedom. So I'm just putting that down here as a subscript. And then you got to get the confidence level right, times the standard error of B1. So the standard error B1 we just computed. B1 we have from our slope estimate, and then T critical value. Now how do you get the T critical value? Inverse T. And you want 95%, so you would enter 0.975 and then 398 degrees of freedom. Now with that big a degrees of freedom, this is pretty much going to be 1.96. Right? It may be 1.98 or something like that. 1.965 something?
Yeah.
Okay.
It's staring at the wall.
The camera.
Oh. I don't know why it's getting lost. Sorry about that. The camera's not tracking very good. Okay. So that gives you a confidence interval for slope. Now let's talk about this analysis of variance table and finish that discussion. And to do that, rather than me write them all out to save time, I've got their PowerPoint presentation. If I can get it to move. There. Ooh, that's not good. It's not really quite showing the whole screen.
Yeah, you have that side menu open.
It seems to want to center more than what I have room for. So we're not quite getting everything, but it's close enough. So the ANOVA table, which you saw in SAS, has this term source. And what that means is source of variability. People's heights vary, don't they? What are the sources of that variability? Well, some of it is due to the model that we fit. the regression onto shoe size. So in other words, some of the variability can be explained by their shoe size, but not all of it. And what can't be explained by shoe size is called error, right? Or residual. The total amount of variability in shoe or in height we call sum of squares total. Right? I think I accidentally did a drag of a piece here and I got that off center. Let me see if I can. Nope, that was okay. So this doesn't seem to be lined up just right, but it's okay. So sum of squared error is exactly what we wrote a minute ago. The sum of yi minus y hat I, quantity squared. The mean square is always the sum of square for that row divided by the degrees of freedom in that row. So degrees of freedom for error is n minus 2. So now let's look at total sum of squares. Total sum of squares is total variability in y. Ignore the x variable. So it's just like you're computing the variance of the y's, ignoring the x. It's y bar or y minus y bar. Right? Quantity squared. Sum those up. If you divide by the degrees of freedom, what do you got? This thing on the top, n minus 1 on the bottom of a fraction. What is that an estimate of? What is that the formula of? You know, I think I can write on the top of this now. Let's see. So, sum of yi minus y bar squared divided by n minus 1. Doesn't that formula look kind of familiar? What does it look like? Standard deviation, only there's no square root, so variance, right? Variance of the y's. That's what the mean square for total would be. SY squared. Right? SY squared. So that's completely ignoring the x variable, just what's the overall variability. That's what variance computes, variability. If I take the square root of it, I got the standard deviation of the y's. But what this table tells us is that the total sum of squares, the total variability in y, is a sum of the variability due to the model plus the variability in the errors, the residuals around that model. So that leaves us SSM. What is SSM? Well, look at the formula for it. Tell me what those pieces are. Y hat I is the predicted value minus y bar, the average of all the y's. Okay? So let's go to a blank sheet here. Draw a little scatter plot. There's my model. A linear equation, right? So y hat I is always going to be on that line. So let's say I have x values at certain places along here. My predicted value is going to be on the line above each of those little tick marks. And I'm getting too close and drawing points sometimes by accident, but all the points are on that line. Now the observed values, the yi with no hat over it, no bar over it, are the observed values. I've already made one there by accident, so there. Okay? Now where's y bar? Y bar is the mean of the y variable. It's the y coordinate of the centroid, right? The line must go through the centroid, so it's probably about right there. I'm going to draw a dotted line as best I can. It kind of got a little curvy there at the end. That's a straight horizontal line, right? So what is sum of squares do to model? Computing. The total variability in the y's is each yi minus this horizontal line, right? Yi minus y bar. And then I square those up. But the sum of squares due to model doesn't use the yi, it uses yi hat. Remember the formula for it? Keep forgetting I can do this. Yi hat minus y bar. So here's a point, right? Here's y hat. So the distance between there, I take that distance, I square it, and I sum those up. So it's always on the line. Those dashes are the yi hats, not dashes, vertical lines, are the yi hats minus y bar. I square each of them. These down here are negative. These up here are positive. I square them, sum them up. That's sum of squares due to model. All right? So the overall variability of a point from this line, get real fancy, use a different color. Like, think of this point. The total variability of this point from the mean of the y's is that distance. It can be then partitioned into two pieces. The piece that I predicted according to my line, plus the piece that was left over due to error. And that's the point of this ANOVA table. The sum of squares total is the sum of the sum of squares due to the model plus the sum of squares due to error. You can sum those two things together. All right? So on a test, if I give you an ANOVA table to fill in, I'll give you one of those three, or give you two of those three, and you get the other one by subtraction. If I give you the error and the total, you can get the sum of squares for model just by manipulating this and so on. Okay, so then you get degrees of freedom. For a simple linear regression, which means one x variable, the degrees of freedom for model is always 1. This degree of freedom for model, when we get to chapter 11, we'll learn is however many x variables there are in the model. So if I have one x variable, I got 1 degree of freedom for the model. If I have 3 in there, I get 3 degrees of freedom for model. The degrees of freedom add in exactly the same way that the sums of squares do. So the error degrees of freedom changes if I change the number of x variables in my model. Right? So degree of freedom for model plus degree of freedom for error must equal n minus 1. N minus 1 is always the degrees of freedom for the total. Okay? Yeah, question?
Okay, so when you were talking about what would be on the exam, you're going to give us numbers for like SST or SSM, and then we're going to derive SSE from the numbers, not that we're going to figure out what y hat and
Right.
y bar.
Yeah, that you could do that theoretically, but it would be a long test. Right?
That would be the test.
Yeah, that would be the whole test. And I'd be testing to see if you could do arithmetic instead of testing to see that you knew how to do regression. Okay, so now the mean square column, we already talked about it. You take the mean, to get the mean square, you take the sum of square, and you just divide by its degrees of freedom. Right? Now let's talk about this guy, the F statistic. Right? The F statistic is the F distribution is like, you know, all these other probability distributions that we've dealt with. The normal distribution, the t distribution, the chi-square distribution. Here's a fourth one, the F distribution. Right? And it turns out that if you take the mean square for model, divide by mean square for error, you get a test statistic to test some null hypothesis. What do you suppose you're testing?
That there is it's a linear relationship or not.
Okay, good. Let me get back to black marker. In words, the null hypothesis is there is no linear relationship between X and Y. What would the alternative to that be? There is a ... all that. Okay? As soon as we get to chapter 11 and we do multiple regression, this F test is not one X and one Y. It's between all of the X's and the Y variable. So a better way to say it is the X variables do not help predict the Y variable. The alternative is they do help predict, right? They explain a significant amount of the variability in Y. Okay? So the F test, actually, let me go to here. They have a slide right here that shows the F distribution. And it's a skewed distribution that is a lot like the chi-squared distribution, but it has two sets of degrees of freedom. Right? So it has a numerator set. So F with numerator df, comma, denominator df. And it's just the degrees of freedom in the thing on the top of the fraction and the degrees of freedom for the thing in the bottom of the fraction. So remember what that F statistic, how we computed it?
MSC divided by MSC.
Yep, MSN divided by MSC. And that one's not it.
It's actually on that slide.
It's on this slide?
Yeah, right above where you wrote.
Oh, yeah. By comparing, yeah, so F is MSM over MSE. So we have mean square for model as the degrees of freedom. That'd be 1 degrees of freedom. Right? And then denominator degrees of freedom would be whatever the degrees of freedom are in the error line of the ANOVA table. And that's n minus 2. Right? So then you either look it up on your calculator with the FCDF function, or you look it up in an F table, or you just let the software tell you what it is. Right? Of course, on a test, I may gray that out and say, figure out what the p-value is here. Right? So look at this null and alternative hypothesis up here. What is it testing? Well, when there's only one X variable, then I wrote it out in words and I said there is no linear relationship. This has beta 1 equals 0. What does that mean? The slope is 0. Okay, say that to your grandmother what that means. If the slope is 0, then
that for every change in shoe size, there is no change in height.
For a change in shoe size, there is no change in height. So in other words, shoe size does not change. Why? Y does not change when shoe size changes. That would be a slope of 0. Right? So it's another way of writing it with mathematical expression, what we said in words. Right? So let me go back to this ANOVA table, and I want you to notice something. Notice this one's not a good one to show, but look at the p-value for the F test. It is less than 0.0001. So what's your conclusion? That there is an association. Okay? Now look at the p-value for the slope. This test is the test of beta 1 equals 0. They are identical. Now just for fun, take your calculator and take this t statistic. Have I talked about where this t statistic comes from?
No, you haven't mentioned it.
Okay, I was thinking I did that last time. But if you take the parameter estimate and divide by the standard error, you get this t statistic. So 1.68045 divided by its standard error, 0.05565, you get 30.2. Right? I'm going to see if real quick I can figure out how to let me write on the desktop annotate. Okay, good enough. No, that won't work.
I think you were writing on it though.
Yeah, but I want to get back to the remote desktop so I can see the SAS output. So now I need to turn that back off. Okay. Okay, so I won't be able to write on it, but let me go back to the ANOVA table. When you square that number, what do you get? 30.2 squared.
Oh, 911.84.
911 point.
Well, I get 84.
Yeah, you get 84 because this has been rounded to two places.
Yeah,
But if we had 10 decimal places for this, right? In fact, do this. Take 1.68045, divide by the standard error. And that's what you did?
Yes.
Okay. And then you square that number, and you should get 911 point something real close.
8.4.
Yeah, it's still 8.4. But what you have to realize is that even at that, we're rounding off. So that's when it's 911.8 instead of 0.7, that's pretty darn close, right? So it's just round off here. So the F statistic is the square of a T statistic if that F has 1 degree of freedom in the numerator. As soon as we go to multiple regression and it's something, then that doesn't hold. But okay, so one more topic in this chapter. And I'm not going to hold you to memorizing the formulas for these things, but I want you to be able to get predicted values and confidence intervals on those predicted values. So if I CL mean, CLI. I'm going to rerun that proc reg, but I'm added a couple of options. P for predicted. So I'm saying give me predicted values, and then also give me. So I'm just, oh boy, 400 observations. So we'll look at the bottom of it rather than scroll to the top. Well, but I can't see, can I? I can't see what the columns are, but this is the observed value, 65 inches tall. This is predicted value. So the model would have predicted they were 64.4. This is going to be the residual. All right, so you subtract those two numbers, you get that. And then this 64.086 to 64.72 is the confidence interval for the mean of everybody with that shoe size. Now, this output didn't show me that shoe size. I could go back and tell it to, but to get the confidence interval for the mean predicted value, there's a formula for that standard error. So that's in their little slideshow here. Right there. Okay, now, I don't know why it scrolled over, but if we want to predict future responses, then that's predicting a response for a single individual. If we want to predict the mean height of everybody with a certain shoe size, then that's SE sub mu hat. Right? So mu hat meaning the predicted mean value, y hat meaning predicted individual value. Okay? So look at those two equations. And let's I got to hurry, but this S is what I call SE. Right, so that's SE, they just use an S. And then 1 over N plus X star minus X bar. So what is X star? X star is X where we are predicting. So it'll say like, predict the height of everyone, the mean height of everyone with the size 9 shoe, then X star is a 9. So it's the same number that you plug into the regression equation to get this predicted value. Got it? And then X bar is the mean of all shoe sizes. And then what's this term on the bottom? Sum of X minus X bar quantity squared.
Sorry, perform Donald leverage value, but it's the difference in like how far it is from.
Now this X does not have a star on it. It's summing across all of the X's. If I divided that by n minus 1, what does this piece look like?
The variance.
The variance of the X's. That's the variance of the X, but if I multiply, or if I divide by n minus 1, I can still multiply by n minus 1 and I haven't changed its value, right? So this is n minus 1 times the variance of the X's. So that term could also be alternatively written as n minus 1 times sx squared, which we did the same thing when we were doing the slope thing. All right? So think about it for a second. To get the standard error of a predicted value, there's different pieces that have to go into it. One piece is how much variability is there around the line. If there's a lot of variability around the line, that affects how good my prediction is. So I have my S in there for that term. But then I multiply that by this thing. 1 over n is because, if you remember from the central limit theorem, the standard deviation of a mean is the standard error of a mean is the standard deviation divided by n, or divided by square root of n. So square root of 1 over n times that's the term from the central limit theorem. Then this term, if I have a lot of variability in my x's, this actually gets small, doesn't it? So this is a factor that says, well, how far away from the mean are you when you're making this prediction? So if I come back to my picture, if I try to predict something in here, and I'm real close to the mean, then having an error in my slope doesn't affect it very much. But if I'm way out here, and my slope is off a little bit, my predicted value has a lot of error. So you get this kind of curved band around the line for these confidence intervals. Right? So the further away from the mean you are, the bigger the error is. So that's what that term is showing. That's this term. How far away from the mean are you trying to predict? If you're a long ways away, then this term is big. If you're up close to the mean, this term is small. Okay. Only thing left is the formula changes when you predict for an individual. It adds a 1 in there. Why would it add a 1?
Like a degree of freedom.
Sort of.
It adds extra error.
You've got the first, to get the predicted value for an individual, you first have to predict, well, what's the mean of all individuals? Now, how much variability around that mean is there for each person? So that's 1 times the standard error, the residuals, is adding back in another term for variability of individuals around the line. Right? So these are called prediction intervals. These are called confidence intervals. But then it's just simply y hat plus or minus same t critical value times one of those two things, depending on whether you're predicting a mean or you're predicting an individual. Go. Have a good weekend.
Homework due Monday.
Yes, homework is due Monday.
Still n-2 degrees of freedom.